In this video, we're going to talk about how do we multiply two matrices. So how do we define a formula for A times B? Okay, so this is going to be a little bit more complicated than adding two matrices or scaling a matrix by a real number like we saw in the last video. So I want to begin with a motivation for where the formula comes from and then look at some examples. So to get a feel for this, let's first consider what happens if I were to take something of this form, where I have A times B times a vector x, and break down what happens with this step by step. So let's say that the vector x is in Rp. Okay, so what I want to do is, I want to first draw a circle to represent Rp, and x is a vector somewhere in here. So x is a vector somewhere in Rp. So what happens to x is first x gets multiplied by b. So first x gets multiplied by b. Okay, and when that happens, we'll get a new vector. We'll get the vector b times x. So let's say that b times x is in another circle. And let's just say that this circle is Rn. Okay, so what we've done here is we've taken the vector x, multiplied it by b to get the vector b times x. Okay, so doing this, multiplying by b, that's the same thing as thinking of this as a linear transformation, which I'll call T sub b. So the linear transformation T sub b has domain Rp and codomain Rn. And then if I think about the matrix B and what the size of B is, let's just write B is an n by P matrix. So why? We've talked about how to get the size of the matrix based off of what I saw in the domain and what the codomain was in a previous video. So I'd encourage you guys to pause the video for about 30 seconds or a minute and make sure you understand why. And if you have a question about that, definitely feel free to ask on Piazza. Okay, so let's keep going. Okay, so far what we've done is we've multiplied x by the matrix B. Now what I want to do is I want to multiply that by the matrix A. Okay, so I want to multiply this B times x by the matrix A in front on the left. Okay, so what's going to happen is, so B times x, that vector, is now going to get multiplied by A on the left-hand side. So I'll get A times B times x. So let's say that this is inside of Rm. So the vector A times B times x is inside of Rm. Okay. So I forgot to mention this earlier, but B times x, we can think of this is the same thing as taking the transformation T sub B and then plugging x into that. So in the same way, I can write what A times B times x is. But before I do that, let me just point out that when I multiply by the matrix A, I can think of this as the linear transformation T sub A. So I can think of matrix multiplication as a linear transformation. And that linear transformation T sub A has domain Rn and codomain Rm. And because of that, A, the matrix that's associated with it, is an M by N matrix. But make sure that you see why. Just like over here, just like with B. Make sure you see where the size comes from. Okay, so coming back to what's happening with this vector, A times B of x. Well, what's happening now is we're multiplying the vector Bx by the matrix A. But we can think of that in terms of linear transformations. Like multiplying by A is the same thing as plugging into the transformation T sub A. And what is it that we're plugging into T sub A? Well, we're plugging in Bx. But Bx is the same thing as, in linear transformation form, T sub B of x. Right, because we saw that over here in the green section. Okay, so we've actually stumbled on something really important, which is that when we multiply two matrices, A times B, that should be the same thing as composing their linear transformations, plugging T of B into T of A. Okay, so I want to state that key observation. So when I multiply two matrices and then multiply that in turn by vector x, like we're noticing here, that's the same thing as doing T of A composed with T of B and then plugging x into that. The next fact that we're going to state is something about compositions, which is if you take two compositions, that in turn is a linear transformation. So that this is true as long as T sub A and T sub B are both linear, and in this case they both are, because they're both associated with matrices, and linear transformations that are associated with matrices are linear. Okay, so now I'm not going to prove this fact, but this is something that is pretty quick to show. So I'm just going to go ahead and use this. So how do we use this observation? So we know that A times B is associated with the composition of these two transformations. So to get the matrix, to get a formula for A times B, I'm going to try to define a formula. What I need to do is find the matrix that goes with this transformation, aka to find the standard matrix of T of A of T of B, of that composition. But we know how to find a standard matrix. What we do is we plug in all of those columns of the identity matrix into it. So let's start that process. So let's take this transformation T of A of T of B and plug in the first column of the identity matrix. So E sub 1. Okay. So let's think of this in terms of matrices. So this is the same thing as A times B times E sub 1. Thinking about it in terms of matrices. But what's B times E sub 1? So let's first remember that E sub 1 is the first column of that identity matrix. It's 1 followed by a bunch of zeros underneath it. That's what E sub 1 is. So when we multiply B times E sub 1, if I think about B in terms of its columns, as B1, comma, da, 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 up until B sub, what's the last column of B? Well, I know from up here that B has P columns, so I go until B sub P. And then when I multiply that by E1, which was 1, and then zeros all underneath that, what I get when I multiply a matrix times a vector is I get a linear combination of the columns of the matrix where the weights are the entries of the vector. So the 1 is going to multiply B1. And then the zeros are going to multiply the other columns of B. So when that happens, I'm just going to be left with B1, because everything else becomes 0. Okay, so we still have the A here, but B times E sub 1, we just noticed, is B sub 1. It's the first column of B. So that's kind of nice. It simplified pretty nicely. So if we keep going like this, we would keep plugging in these E sub i's into our transformation until we get to the last one. So the very last one we need to plug in is, well, the domain of our linear transformation is R sub P. So we'd plug in E sub P. That's the very last of these EI's that we'd plug in. So for the same sort of reason, this becomes A times B times E sub P. And E sub P is going to be the last column of the identity matrix. We'll have a bunch of zeros at the top and then a 1 all the way at the bottom. So the A is still going to be in the front, but when I multiply this vector, E sub P times B, I'll only be left with the last column of the matrix B, which is B sub P. Okay. So now we take these vectors, and these are going to be the columns of our standard matrix. So let's go ahead and write down our standard matrix. Okay, so I'm going to call this A times B. I'm ready to define what it is. So the first column of it is going to be A times B sub 1. The next column would be A times B sub 2. Dot, 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 until the last one, which is A times B sub P. Okay, so this is going to be our formula for matrix multiplication, for multiplying matrix multiplication, multiplying two matrices together. Okay, so let me just point out, a key observation about the sizes of all of these matrices. So if I scroll up a little bit more. Okay, so I know that A from up here is m by n. So A is m by n. B from up here above is n by p. So for a matrix product to be defined, these numbers in the middle, so the n here and this number here, they have to be the same. If they're not the same, the product is not going to be defined, as we'll see in an example in just a couple of minutes. Okay, but as long as those middle numbers are the same, the product will be defined. So when I look at this product, I can easily see how many columns it has. It has p columns. And how many rows does it have? Well, if I look at any of these vectors, like if I look at this last vector, multiplying a times this vector b sub p gives me a linear combination of the columns of a. But the columns of a each have m rows. So this vector is also going to have m rows, or m entries. Okay, so there are going to be m rows in this whole matrix right here. Okay, one easy way to remember what these sizes are is, I sort of think about it as these n's sort of cancel. When those numbers in the middle are the same, they sort of cancel, and I'm left with the m and the p. So this is not a reason why it's m by p. The reason why is what we explained before. It's just a quick trick to remember what the size is going to be. Okay, so let's do an example. Okay, so here's the example. Let's compute the product of these two matrices using this definition of A times B. Okay, so the first thing that I want to do is I'm going to check that the sizes sort of match up and work out. So this first matrix has 2 rows and 3 columns. The next matrix has 3 rows and 2 columns. So I know that when I multiply these together by the sort of trick that I showed you guys, okay, it's going to be defined because these middle numbers are the same. And then if I sort of cancel the 3's out, what I'd be left with are the 2 2's. So my product should end up being a 2 by 2 matrix. So let's make sure that happens. Okay, so if I multiply these using my formula, what I need to do is, so if I think of this first matrix as A, what I'll do is I'll take A times the first column of the next matrix, which is 1, 0, 1. And then I'll do A times the next column of that matrix, which is -1, 2, 1. And I just keep going like that until I get done with all the columns of the second matrix. But at this point, I'm done, because it only has 2 columns. Okay, so now we have to compute what A times 1, 0, 1 is. So multiplying a matrix times a times a vector, we now know 2 ways of doing this. So one of the ways is I form a linear combination of the columns of A. So the first entry here is a 1, so I'd get 1 times the first column of A, which is 1, 4. And then the next entry, the vector is 0, so I'd get 0 times the next column of A, times 2, 5. And then finally plus the 1 times the third column of A, which is 3, 6. And if we add these together, I'm going to get 4 for the first entry, and then 10 for the next entry. Alright, so now I got to do the same thing to figure out the next column, which is A times -1, 2, 1. So if I form a linear combination in the same way, I'll get -1 times the first column of A, plus 2 times the next column of A. Maybe let me put the 1 here, just so it's clear. 2 times the next column of A, plus 1 times the last column of A, 3, 6. And if we work this out, what we'll get 6, 12. 6, 12. So at this point, we are ready to write down our product right here. So the product of A and B, the first column ended up being 4, 10. The next column ended up being 612. And that's our answer. Okay. So I mentioned, actually, I don't know if I said it, but I at least wrote it down at the start of this example, that this is called method 1. At least I'm calling it method 1. So that sort of implies there's another way to do this. And indeed there is. So there's a second method, which is called the row column rule. And this method is going to be quicker usually. And we will talk about this in the next video.